This is a tutorial on statistical methods for peak fitting. My name is Alexandra Larsen, and I'm a PhD student at North Carolina State University. This video will introduce you to peak fitting, a common analytical approach for analyzing spectroscopic and diffraction data for materials characterization. Specifically, I will compare the most common approach to peak fitting involving least squares minimization to a new method using Bayes' theorem combined with a sampling algorithm. These two methods are fundamentally different, and I'll walk you through their differences and similarities. This video is the result of a collaboration between NC State University and the University of New South Wales in Sydney, Australia, and is a product of an award from the National Science Foundation through the International Research Experience for Students program. First, we'll briefly review how peak fitting works. Here is a simple example of peak data that we'll use throughout the tutorial, where we have some independent variable on the x-axis, a dependent variable on the y-axis, and their relationship forms a single peak. If, for example, we were working with a single peak from an X-ray diffraction analysis, x would be our scattering angle, and y would be the corresponding intensity. First, we select a model for the data. A model mathematically represents the key pattern in the data, like the peak we see here. In general, there are several models for peak data that vary in peakedness, including the Lorentzian and the Gaussian. The model we'll select for our data is the Gaussian. It's governed by 4 parameters that each control a different feature of the model. The offset is where the curve intersects the y-axis. The interior is the area underneath the curve. The center is the centermost point of the curve, and the width controls the width of the peak. For brevity, we'll refer to these modeled parameters collectively as alpha. Changing the values of alpha will produce different Gaussian curves. For example, if we changed these by decreasing the offset, increasing the interior, moving the center to the left, and decreasing the width, we'll see a curve that looks like this. This alpha has produced a curve that is not as representative of our data as the red curve, but perhaps could describe a different data set with a Gaussian peak. The goal of peak fitting is to develop an understanding of the alpha values for our particular data set, whether that is providing a single estimate of each or the most plausible range of values for each. In a materials characterization setting, we are interested in knowing alpha, as that is what allows us to understand the properties of our material of interest. In this tutorial, we'll discuss 2 methods for conducting a peak fit. Least squares minimization is commonly used in materials characterization problems. It's typically implemented via Levenberg-Marquette, simulated annealing, and genetic algorithms, among others. Bayesian sampling is a relatively new idea for conducting peak fits in characterization problems. In this tutorial, we'll briefly go into how each method works and how to interpret the results from each. To begin our discussion of least squares minimization, recall that previously we saw that different values of alpha produce different curves, and while the blue curve may work for another data set, it's not exactly capturing the pattern in ours. In least squares, we say that a curve does a good job of capturing our data, like the red curve, is a good fit, and the goal is to search for the values of alpha that produce the best fit. It does this by asking the question, which values of alpha produce the least amount of error? Let's define exactly what we mean by error. For a given value on the x-axis, say xi, there is a corresponding observed value. Let's call that yi. If we fit a curve to the data, we notice that xi corresponds to a different value of y. Let's call that yi hat. So for each xi, there is a discrepancy between the actual observed value and the fitted value we get from the curve. We call this the error for xi. This is the amount by which the curve missed our observed value. We want a curve that gets as close to all of the observed points as possible, so we need one with parameter values that minimize these errors. Least squares minimization looks at the sum of all the squared errors for each xi and finds the value of alpha that makes this quantity as small as possible. We call these the least squares estimates of alpha. So Least squares parameters produce a curve that has minimal error, that is, the best fit curve. Bayesian analysis takes a different approach. Instead of looking for alphas that minimize errors and produce a best fit curve, this method addresses the question, given the data, which values of alpha are the most plausible? So what do we mean by most plausible alphas? The set of alphas that are on the left lead to a curve that doesn't represent the data, so it is unlikely that they are behind the curve of best fit. The set of alphas behind this red curve produce a much better fit, so we could say these red alphas are more plausibly behind a good fit. Bayesian analysis employs Bayes' theorem or Bayes' rule to find the most plausible alphas. Let's break down each component of the formula. P is a function that denotes the probability of. P of A is the probability of some event A happening. Bayes' rule solves for the probability of A given B. That is, the probability of some event A happening, given that we know B. So Bayes' rule says the probability of A given B is equal to the probability of B given A times the probability of A and divided by the probability of B. Let's do a quick example to become familiar with how this works. Let's say we have a dice, and we'll let A be the event that a 4 is rolled. We'll let B be the event that an even number is rolled. So, the probability of A is just 1 over 6, since we are equally likely to see a 4 out of all the 6 possible sides. The probability of B is the chance of seeing 2 or 4 or 6 out of the 6 possible sides, so we get 3 over 6, which simplifies to 1/2. Let's look at the probability of A given B. This is the probability of observing a 4 if we know that we're either going to roll a 2, 4, or 6, so there is a 1 in 3 chance of that happening. We can also use Bayes' rule to find the probability of A given B. We've already found the probability of A, that's 1 over 6. Same with the probability of B, that's 1 over 2. The probability of B given A is the chance of seeing an even number if we know we're going to roll a 4. Well, since 4 is even, we know that the probability of B given A in this case is just 1. So we have 2 over 6, which simplifies to 1/3. Okay, so how do we actually use Bayes' rule to conduct a peak fit? Notice that we can frame the Bayesian sampling question in terms of Bayes' rule. We're looking for the most plausible values of alpha given the data. So we can use Bayes' rule to address this question. If we look back at our red alphas that produce a nice fit as compared to our blue alphas, Bayes' rule is involved in computing and contrasting the likeliness of the two. In a follow-up video to this tutorial, we'll begin to talk about how to formulate each piece of Bayes' rule. For now, we'll briefly go into the sampling procedure for our Bayesian analysis. To conduct a peak fit using Bayesian methods, we use what's called a sampling algorithm. This is because, unlike our dice example, we can't use simple math to compute the probabilities regarding alpha, given the data. Instead, we must use the technique of sampling, where we draw many samples from the probability distribution of alpha given the data, or the posterior distribution of alpha, using Monte Carlo simulation. We can then use those samples to approximate the posterior. We'll cover these processes in detail in a subsequent tutorial, but for now, let's look at a simplified version of the algorithm that we use to conduct the sampling procedure. First, we choose an initial guess of alpha along with upper and lower bounds. Next, we pick a new alpha, or candidate alpha. Finally, we assess the candidate. So, if we accept an alpha, we store it in a histogram, and if we reject the alpha, we discard it. So, for the example we've been using, our red alphas will accept, and our blue alphas will reject. We iterate through this procedure thousands of times for each alpha: offset, interior, center, and width. This video illustrates the iterations for fitting our simple Gaussian peak dataset. In the top panel, the red points are our observed data, or measured data. The fixed black curve is the least squares curve of best fit, and the changing curves are being produced as a sampling algorithm considers each candidate alpha. The curves are green if they were made by an accepted candidate and red otherwise. Each time we see a green curve, the histograms in the bottom panel are populated with an accepted candidate for each alpha. Now that we've covered each peak fitting method, let's look at some results from using each on our simple peak data. From running least squares, we find that these values of alpha minimize the error and produce this fit. For our Bayesian method, we get histograms from the sampling procedure for each alpha. Histograms present a lot of information about each parameter of interest. We can examine measures of centrality, like the mean or average alpha value, and the median, or middlemost value. Notice that in this example, the average and middlemost values are practically the same, so we could use both to summarize centrality. In the case that a histogram is asymmetric, however, the mean and median will be different. Means are sensitive to outliers and do not summarize the centrality of skewed histograms very well. Medians are more reliable measures of centrality, as they are not affected by asymmetry. We can also examine the spread of each parameter by examining the standard deviation. The distance between the center lines and the dashed lines mark one standard deviation from the mean. This describes how concentrated the distribution of the histogram is around the mean value. In the results from both methods, it is important to report measures of uncertainty, like a confidence interval for least squares and a credible interval for the Bayesian analysis. The definition for a confidence interval is: if we repeated the study a number of times and computed a 95% confidence interval for each study, then about 95% of them would contain the true alpha value. A confidence interval tells us that our method produced a precise estimate if the interval is narrow, and a less precise estimate if the interval is wide. We can also say that we are 95% confident that the true value we're trying to estimate lies within the interval. Note that we are 95% confident does not mean we believe there is a 95% probability that the true value is within the interval. The 95% stipulation pertains to an anticipated frequency of occurrence, not a definite probability of occurrence. This is a common misconception about confidence intervals and can lead to over or underemphasizing the meaningfulness of some results. The definition of a 95% Bayesian credible interval is, in fact, that there is a 95% probability that the 95% credible interval contains the true value. This interval also conveys information about the precision of our estimate. The narrower the width of the interval, the more precise our estimate is. The interpretation of a 95% credible interval is that there is a 95% chance the true value lies within the interval. Here we have a comparison of the results. From the Bayesian methods, we get histograms that convey information about the behavior of each alpha value. The average for each is denoted in orange, and we have credible intervals outlined in dashed lines. Below each histogram, we have the least squares result, a single point estimate with the corresponding confidence interval. This concludes our coverage of peak fitting methods. As we can see from the results of our example peak fit, if we look at the summaries from the Bayesian method, they convey similar information to what we would see from least squares. However, where least squares only provides a single estimate for each alpha, the Bayesian method produces histograms that give insight into ranges of possible values for each alpha. In a subsequent tutorial, we'll cover the Bayesian method and the sampling algorithm in more detail. Thanks for watching.